finally. So at least Abby will not have missed much. Okay. So continuing with interpolation. All right. Now, so the whole point of today, or most of today, is what if all of the x values that we have are not distinct? That seems like a strange assumption because if you have all these data points, why would you list any of them twice? Because it still has to be y being a legitimate function of x. So if you have, for every x, there has to be only one y value. So if we're going to have two x's being the same, we're also going to have two y's being the same. But here's something to keep in mind. So I'm going to ask a slightly different question. What happens to our interpolating polynomial at this point, at a certain point xi? Okay. Well, I started late. So,
hurry it up, the hurry and the hurry.
Yeah, so you've missed practically nothing.
Yeah.
That's what it would like.
Okay.
Yeah.
Some pretty breathers.
Okay. All right. So what happens to the interpolating polynomial at a certain point xi? So fixed I here. As the next point, and we'll assume the points are in order, approaches xi. Okay. Because what ends up happening is, like if we take the limit as xi plus 1 approaches xi, so these x values are approaching each other, and therefore the y values have to be approaching each other also. But these are also values of the interpolating polynomial. So I'd have to fill in Pn of xi plus 1 minus Pn of xi minus over difference in x's. But what is that? What's that going to be? No. Slope, also known as derivative. Yeah. So Pn prime of xi. Okay. All right. So, but the thing is, we have this polynomial of degree n for n plus 1 points. But now we're saying that two of these points are going to be the same. Now, what we had before was we assumed all the x's were distinct. And we showed that the interpolating polynomial of degree n is unique. Now it's not unique anymore. Because we only have one fewer point to fit. But we still have degree n, fitting n points instead of n plus 1. So what we can do is to ensure uniqueness, we have to specify a derivative value. So like yi prime. All right, so that way, even though we no longer have n plus 1 distinct x's, we still have n plus 1 constraints on our n plus 1 unknowns, the coefficients. So really, we're just swapping one constraint for another. So we still have a unique interpolating polynomial. Okay. Now, so to be a little more general, if a certain x value is listed a certain number of times among your interpolation points, then again, to ensure uniqueness, you have to specify all the derivative values at that point, like so y value, y prime value, double prime, and so forth, all the way up to derivative number k minus 1. So you still have k values or k constraints. So as long as you have that information about your function, then you still have a unique interpolating polynomial of degree n. Okay. Now, doing this kind of interpolation, where you start listing x values more than once, is called oscillatory interpolation. So as opposed to what we talked about on Monday, where you required that all the x values were distinct. Okay, so just as a definition, just when you have repeated x values, and therefore you need derivative information. Okay, and the name oscillatory comes from Latin. So the verb oscillare is to kiss, because then you have these points coming together and meeting. Okay. Now, what I'm going to focus on now, though, is a particular kind of oscillatory interpolation that's frequently used, where you list every single x value twice, and therefore for each x value you have a y value and you have a y prime value. So you're specifying first derivative across the board. And this is called Hermite interpolation. So Hermite interpolation is you're given, now you have n plus 1 distinct x values once again, but you're also given corresponding y values like before, and I'll check my notation here. All right. Well, y prime values. Okay. So you find the unique interpolating polynomial now, let's see. I wonder if I could call this something else. Yeah. Okay. Now the thing is, we have n plus 1 x values. We also have n plus 1 function values and n plus 1 derivative values. So when we didn't have derivative values, my polynomial would be of degree n. What should the degree be now in order to satisfy all of these conditions? 2n plus 1, because
N plus
you have n plus 1 constraints here, n plus 1 constraints here, 2n plus 2 constraints. That means 2n plus 2 coefficients from degree 0 up to 2n plus 1. Yeah, so 2n plus 1 that satisfy that. So you plug in each x, you get the corresponding y, and then you plug in each x into the derivative of your polynomial, and you get the corresponding derivative value. Okay.
Wait, I got a question. You said n plus 1 and n plus 1. You add those together, right?
Yes. And
Yeah, that would be 2n plus 2.
yeah, it is 2. It is 2n plus 2.
Oh!
Yeah.
That makes sense.
Yeah, just like on Monday. Yeah.
Cool, okay,
Okay.
yeah, perfect.
All right. So what we'd like to do is something similar to Lagrange, where we have these polynomials that satisfy, certain conditions, and we just combine them with these y values here. Now, actually, I'm going to, just for agreement with my notes, we'll assume that these y values come from some function, whether that's known or not. And therefore, the derivative values come from a derivative of that function. That way, I can just use f and f prime in the rest of this, and we're all on the same page. Okay, so we want to have as much as possible this polynomial, the Hermite interpolating polynomial, have a similar form to the Lagrange one that only cared about y values. But because we need to match derivative values too, that's going to create a bit of a challenge. Okay. So I'm going to write down what I want the form of a polynomial to be, and then we'll figure out how to make it work. Okay. So we'd like to have a linear combination of polynomials. Where the coefficients are just our function values and our derivative values again, kind of like a Lagrange case. So like the start of this would be almost exactly like a Lagrange case. So your y values, your f values, times, but I'm going to call something else here, hi of x plus f prime, your derivative values, times some other polynomial, which I'll call ki of x. So the idea is these h's and k's play the role of Lagrange polynomials, but I'm not going to use actual Lagrange polynomials because these have to satisfy different conditions than Lagrange. Okay, so what conditions will they satisfy? So these have to satisfy these conditions. First conditions actually are Lagrange-like. So if I plug in an x value into an h, it must equal 1 if I equals j, and 0 otherwise. So you might be thinking, oh, well, that's Lagrange. Well, yes, those are the Lagrange conditions, but we need more. We also must require that if we plug in any x value into the derivative, it has to be 0, no matter what. So okay. So this is why we can't use Lagrange, because Lagrange polynomials, they'll satisfy these, but not these. So in fact, we can see why the degree of hi has to be 2n plus 1, because we have again we have 2n plus 2 constraints. We have constraints on the value of the polynomial itself. We have constraints on the value of the derivative. 2n plus 2 constraints in all, and it takes a polynomial degree 2n plus 1 to satisfy it. Okay. So that way, if we plug in any of our x values, like xj in here, then this will pick out the right f value. And if we take the derivative of this, that means we're differentiating the h's. Well, those will just be 0. So they won't get in the way. Now, what about the k's? Because notice these are multiplied by the derivative values. We want to make sure that if we plug in an xj into here, whatever we get is not going to be polluted with derivative values. Also, if we take the derivative of this and plug in an xj, we get the proper f prime value. So, what conditions similar to these should I impose on the k's?
Is it not the same conditions?
Not quite. They're similar.
Instead of this derivative, just the function
What?
equal to 0.
I'm sorry, what?
Instead of the derivatives equal to 0, we have to set function equal to 0.
Yes, I think it's what you also said. Yeah. Yes. So this must be 0. No matter what. Okay. And then we have something like this. It's kind of Lagrange-like for the derivative. So ki prime xj. And that will be 1 if I equals j, and 0 otherwise. All right.
Will you explain to me why that's 0, the first part?
Oh, here?
Yeah.
Because, all right, let's suppose we plug in xj up here.
Okay.
We want the output to be f of xj. So,
Completely?
and this part will work, because this will be 1 at xj.
Oh, so we need the other part to 0 out.
Yeah, we want this to
Just
not get in
f
the
of
way.
x, j.
Yeah,
Okay.
yeah, we're like, all you do is get out of here, shoo.
Okay.
Yeah.
Where does that ki prime go? Like, where does that go?
When you take the derivative of
Yeah,
These,
yeah.
We're not like plugging in.
No, because we don't, this doesn't step up until we differentiate this whole thing.
Okay.
Yeah.
Okay.
And when we do differentiate this whole thing, we're going to be picking up these guys' derivatives too, but we make them 0.
Oh, so then we're only left with f of prime.
Yeah.
All right.
Okay. Amber, do you,
Yeah. Yeah.
okay.
Sorry.
No problem. Okay, all right. I saw Vivian's light bulb go on, so I'll make sure the light bulb is going all the way around. Okay. Now, okay. So now I'm going to it's not going to violate what I talked about in Math 500 this morning and go off script. Because one thing that I've tried to do ever since teaching numerical analysis here at USM is that certain things I learned as a student, certain facts or theorems, I would take for granted. I was like, well, no, as a professor now, I should be able to just prove it. And in many cases, I did. Now, I have formulas for the h's and k's in my notes, and we'll get to them, but I want to see, it'd be nice to like simply come up with them. Because I can show you the formulas and you can confirm that they work. But instead, like if you don't know them at all, how would you derive them? Can we do that? Is that possible? And I'm not sure if it's going to work out, if we might find it too hard and suck up all our time and fall behind. And therefore not be able to ask you guys anything for weeks to come. So I thought that might appeal to you. All right, so let's see if that's possible. So I'm not even going to look at my notes. Just from what's here, because with Lagrange, that's something that's possible. You can say, oh, it's 0 at these points. We have, so we know something about the roots and we know where we want it to be equal to 1, so it kind of all falls into place. It wasn't that hard to do. But this is going to be harder, of course. So, and I think the easier thing to do would be to focus on the k's first. I just have a hunch it might be simpler. Because one thing that applies to both the h's and k's, we know a lot about the roots. Because when a function is equal to 0 at a point, and its derivative is 0 at a point, it's a double root. And what that means is, these are polynomials. If a function is, so what does it mean about the factorization of a polynomial if you know it has a double root? So if it's,
Factorization of it, is that what you said?
yeah,
If
factorization.
it's gonna be something squared.
Yes, it's going to have something squared. Yeah. So what we know about k I of x, this factorization has to include like x minus xj squared for all I not equal to j. Now, what other polynomial includes the factorization x minus xj for all j not equal to I? So everything except 1, which we called the
What do we call it?
Interpolating?
Not the interpolating polynomial?
well,
Not P.
which is built from what kind of polynomial? What's the name for it? Some guy's name.
Lagrange?
Yes. Yes, I totally didn't hear that coming from the other side of a room. Yes, Lagrange polynomials. So, but the thing is, Lagrange polynomial has each factor once. We need it twice. So what do we do?
Square the
Yeah, we just go ahead and square it. So we'll start with polynomial degree n, because we have n plus 1 points, using a notation from Monday, and we'll just go ahead and square that. So that guarantees that these conditions will all be satisfied. Well, actually, at I not equal to j. We haven't taken care of at xi yet. But okay, so these guys, I'm not gonna make a donut here. So that's done, and also this is done at least for j not equal to I. So we have 2n plus 2 conditions all together, and we've already taken care of 2n of them right off the bat. In fact, the same goes for h. Also, it's going to have, so both polynomials start out the same way. But now we have other stuff. So I'm going to put on like another polynomial, say q of x, or qi of x. And I'll call this ri of x. I don't know what these are. So I need these to satisfy the other conditions that still remain. Okay. So that wasn't so hard to make good progress, just by looking at the roots. The roots tell you so much about what you need. Okay. Now, so what we need from here, we need to see what's going on at, okay, we've taken care of everything except when I equals j. So, ki of xi is going to be equal to what? Well, what will this part be equal to? Yes. So all we get is qi of x. And we want that to be 0, or qi of xi. We want that to be 0. And ki prime of xi, well, we need to take the derivative of this. Well, what is the derivative of that going to be?
2 times
Yeah, 2 times Lagrange. Well, what else do we need before we move on?
Times the derivative.
Times the derivative of Lagrange times qi of x, and I'm plugging in xi throughout. Okay. What else? What do I still need?
Plus Lagrange squared times your process.
Okay. And what is it supposed to be equal to?
Over here.
Okay. I didn't hear what you said anyway.
I said don't forget your xi.
Oh, yeah. Yeah, this must be equal to 1. Okay. Now, bless you. This monstrosity here can be simplified a lot.
Well, qi xi is equal to 0.
Yep.
So it's just the second term.
Yeah, so that's gone. So that's nice. And
And then that's ki. Can we do? No, just kidding.
okay. What can we,
Is that gonna be? Well, it can't be 0.
well, what can I simplify here?
Is that gonna be at xi? So is that
Yeah.
gonna be 1? So it's just gonna be qi.
Yeah. So yeah, this is 1.
Because Lagrange is 1 at I. Yeah.
So here are my conditions. Qi of xi must be 0. Qi prime at xi must be 1.
I feel a trig coming on, some kind of cosine or sine or something.
No.
Forget I said it.
Oh, because of the 0 and 1?
Yeah.
Okay. Alright. Now the thing is, we need this polynomial to be of degree 2n plus 1. Well, Lagrange squared is already of degree 2n. So we only have 1 degree left over for this. So it's going to be a linear function. And a linear function has 2 coefficients. We have 2 constraints, so that works out perfectly. So what is the unique linear function that would satisfy both of these conditions? Well, if you have a linear function, what's the derivative give you?
Just a constant.
Or what's the meaning of a derivative? Yes, it is a constant. What's the meaning of a derivative? Slope. Yeah. So x, well, that's part of it.
Oh, the slope is 1.
Yeah, the slope is 1. So in fact, we could integrate this and we get x plus c. But we need to make sure, okay, so this is done. But what about this condition?
Plus.
How can I make sure that the one and only root of this linear function is that? Just so something like this. Well, at xi. So plug in x equal xi and make sure you get 0.
So
No, you know, a constant.
What? No. I couldn't hear you.
X minus xi?
Yes.
You right, girlfriend?
speak up.
Yeah. Yeah.
X minus x. I said x minus x, and I was like, that's all we're
Yeah, talk about overkill.
Yeah.
Yeah. So there you go. So now we can go back and fill this in. X minus xi.
Oh, we said slope.
What?
Nothing.
Well, my hearing's awful.
I talked to myself. I was talking myself through it.
Okay.
It wasn't meant for like a class discussion.
Oh, okay. All right. Okay. Well, so we came up with it. Or at least that one. We still have the other one.
It'll be easier.
No. From what I remember of the formula.
Okay. Just kidding.
All right, but do you see where k comes from?
Yeah.
All right. Now, the way we can get this is similar because really it's just going to be the opposite conditions.
Yeah.
So,
R equal to 1, R prime equals to
yeah, so R, yeah. Well, actually, no, hold on. No, it's not going to be like that. Okay, if we plug in x equal to xi, that'll be 1. Okay, so we do have this. Ri of xi equals 1. But now, because your differentiation is going to be much like this term doesn't go away.
But it's equal to 0 this
Oh,
time.
because it's equal to 1, but the other one's equal to
This
0.
part is going to be equal to 1.
So you're left with.
No, I'm saying the whole thing is equal to
Yes.
0.
Yeah, the
So
whole
it's
thing is
little.
0. Yes.
Yeah, so we'll be able to solve this.
Yeah, so now let's fill all this in. So we have 2 Lagrange at xi squared Lagrange prime at xi ri of xi plus Lagrange at xi squared ri prime at xi must equal 0.
You're missing a.
Right.
Yeah, you got a squared and you're missing a prime.
That
That.
circular without.
The squared 2 goes away.
Yeah. Okay. This is why I don't go off script. I shouldn't go off script. But why not just stop me?
Now this is equal to h I of x I or h prime? H prime. Okay.
Yeah, h I prime. That's why it's equal to 0.
Okay, yeah.
Okay, but now in this equation, what can we simplify?
Although
The bottom
the
part.
second term,
Yeah.
What about it?
Bottom part goes away completely, right?
No.
well, that it would just be the Lagrange squared is just 1.
Yeah.
So then you just get. Wait, don't even. I haven't written any of
It's-
those down.
It's
me
1.
neither.
Well, hurry up.
Okay, hold on.
I'm deep in thought. I can't write anything.
I keep dotting my commas because of the eyes.
Yeah, with the eyes and commas.
Yes.
I don't know.
Okay,
Hard
and
like
then
that,
the
hard.
2 Lagrange. Wait, so
Wait,
that would just
That's not
that's
fair.
0. That would be 1. So you get
What part we want?
just the Lagrange
Yes.
in there, not the
Okay.
prime. That'd just be 2. Well, okay, yeah.
Okay. What else can we simplify? Yeah, but the Lagrange
And that's-
prime we can't do anything with. That's just
We
going to
don't know
stay.
anything about that.
No.
Okay, Ri is 1.
So
So
now,
we have two-
okay, so instead of erasing again, I'll have 2 lni prime at xi plus ri prime of xi equals 0. Okay. All right, good. So, what's my slope?
Okay, so now,
You tell me.
is it not?
I don't have to now.
That is the slope. Yes, it is.
Well,
Well-
ri prime of xi is the slope. This is once again a linear function like q was.
Can we just solve for Ri prime?
Yes, you can.
Just a little subtraction, maybe?
Yes.
Alright,
Oh,
subtract this.
So then is
Okay.
it just -2 Lagrange?
Yes.
Lagrange negative?
Yeah, so therefore ri of x is equal to minus 2 Lagrange prime at xi plus-
Wait, Ri.
Alright, prime.
but
Oh, he's doing it in 2, so he's doing it in 1 step.
times x
Yeah,
plus a constant
Xi.
plus c, so that when we plug in x equal xi,
That is the equal 1.
yes, we have to get 1.
Okay, so when we plug in xi, we have to get 1.
We don't know anything about Lagrange prime?
Yeah.
No, yeah, we have to leave it as that. It's just some number. So yeah, that's going to creep into our final expression.
Okay.
So it's going to be messy, but we can still do it.
It has to equal 1? right?
I
The whole-
don't know
yeah.
anything about the Lagrange prime. Okay.
Alright, well, let's go ahead and plug in xi.
Okay.
Doesn't really help us much at all, but and I prime of xi plus c is equal to 1. So now we use that to solve for c.
Could we divide by the same thing,
Um,
where x has a constant, or is it? Oh, what is
So
c
1
equal?
plus
One
all of that.
yeah,
That's it? Don't tell me that's it.
yes,
And
it's it.
subtract it. We'll add, but you know,
Yes,
make it a positive.
Yeah, so now we can say Ri of x is equal to 1 plus 2 ln, or actually I'll use minus of xi, and I can write it in the factored form, x minus xi. Which reads my notes, good.
Okay, so the original one, so go back to the first,
Yeah,
that note down one. Oh yeah, okay, that's first, that's fine.
Yeah.
So x is in there, and then, but c has xi.
yes.
So is that xi always going to be xi no matter what you plug in? You only plug in for x, correct?
For c.
Okay.
C is a constant, right?
Oh, are you talking
Yeah,
about
yeah.
like when we did
Xi is going
ours?
to be a constant.
Yes,
Because
it is.
otherwise it's going to be 1 for everything.
Yeah, yeah.
Okay.
yeah.
Okay.
That's why in the,
Yeah.
yeah.
Okay,
Cool.
so now I can specify the h's. It's this. 1 minus 2 Lagrange prime xi x minus xi. Yeah, because in the textbook, most formulas for k's and h's, they're just pull out of thin air like, oh, here it is. And now we know we don't have to do that.
That's good.
Now, how much time did I chew up with that? Hopefully a lot.
You got 30 minutes, less than 30 minutes left.
Okay.
I can ask a bunch of questions.
28.
Yeah, Haley's not here. We don't
Okay.
Some thought.
All right. Now.
Next time we'll be like, hey, listen.
Okay. So, because the things what I'm supposed to cover today is interpolation, and also using polynomial interpolation for numerical differentiation. But that's not a short topic. So I guess I'll have to wait till Monday. So I'm now behind. But we have all this room at the end of the semester, so it really doesn't matter.
Yeah.
So, of course, that just means less chance of calling people. Yeah, so I'm sure you're all glad I did this.
Alright, I have a question.
Okay.
Why would we ever be given two of the same x? Is it because it's a double root?
Well, because you have, if you like, it depends on what data you're gathering. Like if you're gathering y values and slopes at those points, then you want to be able to take it into account in constructing your approximation.
Oh,
And
at the
Lagrange-
same x point you're getting the slope and the y value.
Yeah, you're given extra information because Lagrange interpolation would not give you a way to do that.
So they're not really giving us two, because I was like, how is it a function if it has
Oh
two
yeah,
x's and two y's? But that's because one's coming from the function, one's coming from the derivative.
yeah. All right. And the thing is, if we're doing like Newton interpolation, like using divided differences, then we literally would list the points twice, and like once, and take into account the function and derivative values. So that's why we talked about listing points multiple times. Okay. Now, okay. So now what I want to do is prove that if you construct a polynomial in this way, that if you have a polynomial degree 2n plus 1 and satisfies all these conditions, and it matches f and f prime at all these points, then it really is unique. So the idea is going to be similar to how you prove that the Lagrange interpolating polynomial is unique, but because there's derivatives involved, that complicates matters just a little bit. Okay. All right, so I'm going to prove that the Hermite interpolating polynomial is unique. Okay, and we're going to do this kind of by contradiction in a way. So we're going to assume there's just two polynomials, p2n plus 1 and p tilde 2n plus 1. That satisfy the conditions. And you plug in the x values, and it matches f. And same thing for derivatives. Okay. And for all. Alright. And my arm's sweating out from that. Alright, now. So now what we can do is we'll consider the difference. And the idea is similar to how we proved the Lagrange polynomial is unique. You want to show that it has too many zeros, because so the degree of this is 2n plus 1. Okay. So we want to show that it has more than 2n plus 1 zeros, and therefore the whole thing has to be 0. But we have to work it out for us. So for one thing, here's what we know. And it has n plus 1 zeros at all the xi's, because it has to match f at those points. So, okay, so these have n plus 1 zeros right there. Now, we don't know anything else about any other zeros that h has, but what we do know is h prime has n plus 1 zeros at those same points. All right. Now, I'm trying not to look at my notes. I have a proof right there, but I figured I'm a dang tenured professor, I should do this. But it's also the end of the day, and I'm just over it. All right. Because likely the argument would involve like something similar along the lines of Rolle's theorem or whatever. Okay. I know how this is supposed to go. Because we're going to play with the derivative, not so h prime, not h. So if you look at what's going on here at these x values. So we know that h, the difference, is equal to 0 at each of these points. So by Rolle's theorem, h prime has zeros in between. So we have n plus 1 zeros at the x's, and by Rolle's theorem, it has n zeros in the gaps in between. Okay. Because we have n plus 1 points, we have n gaps. So, h prime has 2n plus 1 zeros. What is the degree of h prime?
Two n plus 1 zeros is for
H prime. But what is the degree of h prime? I think someone said it.
2n plus 2n.
2n. Yeah, because h has degree 2n plus 1. We deduct 1. So h prime has degree 2n. So what does it tell us about h prime? The polynomial is a certain degree, but it has more zeros than that. How many zeros should a polynomial degree 2n normally have?
Is it just equal to 0?
Yeah, it's 0 everywhere. So, okay, so h prime is 0 everywhere. But when a function's derivative is 0 everywhere, what does that say about the function?
Constant.
It's a constant. So now, do we have any information that can tell us what that constant is? What do we know about h? That's fact, it's defined to be the difference of these two, but
It has degree 2n plus 1.
at most, yes. But what else do we know about h? That's on this board.
It has n plus 1 zeros.
Yeah, so because it has a 0 at all, but it's a constant function,
Zero means it's
yeah, 0 everywhere. Yeah. Yeah, because h is equal to 0 at all these points, so that means that h is 0 everywhere. Therefore, p 2n plus 1 and p tilde 2n plus 1 are equal everywhere. Therefore, you have uniqueness. Okay. You don't need those sticky notes. Okay. All right. Okay, still 15 minutes. Okay, any questions about that? Oh, I have no need to. I got a perfectly clear board over here. All right. Now, back on Monday, I did that crazy tricky proof that the of our error formula for Lagrange polynomial using a crazy function phi, and using a similar approach, which I won't bother repeating here because it really is so similar, it's not really all that interesting. Okay. the error formula is pretty similar. That because the Urban interpolation polynomial is of degree 2n plus 1, you're going to have the next order derivative of that 2n plus 2 at an unknown point over 2n plus 2 factorial. And whereas before you had all these factors, x minus x naught, x minus x1, etc., you're going to have those again, except because each point is listed twice, they'll be squared. All right. And one convenient thing about that is, if you know something about whether the derivative of f is positive or negative, not only do you have an error estimate, you can determine conclusively that the Urban polynomial is either a lower bound or an upper bound of f. Just because now this part is all is positive. Okay. Well, dang. I finished the Urban section, and there's still time left. But now I have all this differentiation stuff. Okay. All right. Well, I'll run down the most important point anyway. All right. Now, so how do you use polynomial interpolation for differentiation, or at least approximate differentiation? Now we're back to Lagrange interpolation. So Pn is the Lagrange interpolating polynomial, or Lagrange interpolant, at these x values. Bless you. And we're calling it the Lagrange interpolant of f of x, as usual. So what that means is, so f of x is approximated by this linear combination of function values and Lagrange polynomials. So then we want the derivative. So that means that an approximation to f prime at a certain point, let's use x naught from our x values. Now f of xi, those are constants, so that part stays the same. So then we differentiate the Lagrange polynomials, and we evaluate those derivatives at x naught. Now,
Just Jeremy's phone in class.
oh, yeah, so by all means harass him. Now the Lagrange polynomials, most of them will be equal to 0 at x naught, but their derivatives, not necessarily. Generally, they won't be. So, okay. So then, you can think of these values of the derivatives of Lagrange polynomials at x naught. You can think of it being like weights, in a sense. That we're approximating a derivative by taking a linear combination of the function values near x naught and these Lagrange polynomial derivatives tell us how to combine them to get an approximate derivative. Okay. All right. Now, I could actually say something about the error, because from this, like the error formula for Lagrange from Monday, I'll just repeat that error formula. So it's n plus first derivative at an unknown point, or plus 1 factorial, then x minus x naught, x minus x1, etc. Okay. So now, if I want to approximate f prime and x naught, I have a derivative of my interpolating polynomial, because I really should have mentioned this earlier. This whole approximation is nothing more than Pn prime at x naught. Because this right here, and I apologize for my extremely sloppy board work. Okay, the point is, we are approximating everything involving f, we're approximating by Pn of x. So f is approximately Pn. F prime of x naught is approximately Pn prime of x naught. But I just wanted to write it out here so you can see what form it has. Okay. Dang it. Sorry, I'm being extremely anal retentive here, but I can't help it, so just deal with it. That's how it should have been written the first time. Now, I need to take the derivative of this error formula and evaluate it at x naught. And the thing to keep in mind is this unknown point really should be written this way, xc of x. Just to make clear that the unknown point does depend on x. And we have no idea what it is, but there's still a dependence there. Now, if I'm going to take the derivative of this, what would I normally use?
Take the derivative of the right hand side?
Yes, yeah,
F prime.
product rule. Product rule up the wazoo, because I have n plus 2 linear factors here. But here's the thing that saves me from having to actually do all that, because I certainly don't want to take a derivative of that. I have no idea what this is. Because I don't just take the derivative, I also plug in x equal x naught. So when I take the derivative of all this, and that is product rule of a zillion terms, almost all those terms are going to have an x minus x naught in them, which will just cause the whole thing to go away. Except for what? What's the only term that's going to stick around?
You're plugging in x naught?
Yes, for x. Because when I do product rule, each one of these factors, I have a bunch of terms. I'll have n plus 2 terms. And in each term, one of these factors gets differentiated. So, but if almost all of these terms are going to have an x minus x naught in them, the only one that doesn't
That's the one that already has.
is the one where x minus x naught gets differentiated. Because when you do product rule, like if I have three factors here, I get A prime BC plus AB prime C plus ABC prime. It's like that. So basically the product rule takes a whack at each one of these factors. So when it whacks x minus x naught, that's the term that's going to stick around, because you don't have an x minus x naught in there. You differentiate this and you get 1. So what we have is this undifferentiated, and then you have all of these factors except x minus x naught, whose derivative is 1. So it's a product. Well, j equals 0 to, j equal 1 to n. So I'm skipping 0. Okay. All right. So, so if we choose certain points, like choose our x values to be, we pick x naught, that's where we want the derivative. And then we might have a rule like points like x naught plus h, or x naught minus h, or x naught plus or minus 2h. We use some spacing h, for instance. Then we can figure out what the formula is and get an error formula. Because we're using spacing h between all the points, then all these, there should be x naught. Sorry, x naught minus xj. So now, all these linear factors would be like some multiples of h. So we can figure out what that is. And then we still have this derivative, but nothing we can do about that. Okay, I don't really have time to go further. So what?
Is there any difference between xj minus x naught minus x naught? That minus sign.
Okay. Between what?
Isn't it correct to say xj minus x naught instead of that one? I mean, how that minus sign came?
Oh, well, the thing is, I'm plugging in x naught for x.
Okay.
Yeah. Here I'm just representing these factors in a more compact way.
What about xz? Is it still dependent on x, not x naught, or okay? But it's x for just f of x minus.
Yeah.
Everything else is 0.
What's x? What's x now again?
Oh, it's a point at which we actually want a derivative. Because the whole idea is we're not really approximating f prime of x, a function. We're approximating f prime at x naught, a number.
Different points.
Yeah, and the thing is, this will be made more clear on Monday when I go further into this and I come up with specific rules. Like we'll make specific choices about these points. Like we'll use equally spaced points, even though you don't absolutely have to. And I can show you how certain differentiation rules are constructed and how we get more concrete error formulas in this. But I've laid out the approach anyway. So
It's in the f prime minus p and f prime. It's xz at x naught. I don't know if y'all were.
Yeah.
Or just telling them that they
X
put it
naught.
at x naught right there, not just x.
Yeah.
Oh yeah.
okay.
Oh yeah.
Well, it's good you're making sure everyone's paying attention.
Yeah. It's the teacher.
The teacher.
Yeah. Well, yeah, guys, you're only a little bit above high school. Okay.